So Unit 1.2C's example 2 is a really hard problem. I think there's a lot of stuff that has to happen in it. And so if you found yourself stuck on this one or you want to kind of work through it just because you're not sure, I think that's totally appropriate because there's a lot going on. If we read it over, it says in the stratosphere, UV radiation can break down a pollutant called a CFC. UV radiation breaks the C to Cl bond. It takes 542 kilojoules to break 1 mole of C to Cl bonds. What is the wavelength of the radiation needed to break 1 C to Cl bond? So there's a lot of information in this problem. We are given an energy value this time, so it's a little bit different than our previous example. They give us a lot of story here, which is delightful. And one of the things that you're going to find in the AP exam is that they tell you a lot of story. So the hard part about that is picking out what is useful. So they give me this kilojoules of energy. And then when you read through it, it says it's kilojoules to break 1 mole of bonds. Okay, so 542 kilojoules is equal to 1 mole of bonds. So we're going to kind of keep that in the lockbox for our information a little bit later. And then it's asking us what is the wavelength of the radiation needed to break 1 C to Cl bond. So it's asking about wavelength, which is lambda. At this point, you should be cursing the person who wrote this problem, which is me. Sorry about that. We need to tie together energy and wavelength. But if you think about it, we have two separate equations. We have change in energy is equal to Planck's constant times the frequency, and then speed of light equals wavelength times frequency. So they're tied together, but not necessarily, in an easy way, and that can be kind of frustrating. The other thing that we have to pay attention to is that this energy here is talking about 1 mole of bonds. And the question is asking us for 1 bond. Okay? Another thing that's tricky about this problem is that energy is always going to come out in joules, and we are given a problem in kilojoules. So you say to yourself, how many different things can this person ask me to do? And the answer is a lot. This is a tough question. You do see questions like this sometimes on the test, and so we've just got to kind of go over it. So, things that we need to do to attack this problem. We need to get to wavelength. We need to find frequency to put into the equation to get the wavelength. And we need to deal with joules, not kilojoules. We also need to deal with 1 bond, not a mole of bonds. So there are a bunch of different things that we need to kind of take care of. My first order of business, I think, is going to be to take the kilojoules and get them into joules. So that is what I'm going to do first. 542 kilojoules, and I want to convert them to joules. So there are 1,000 joules for every 1 kilojoule. Kilojoules cancel out, and I get 542,000 joules. Okay, now that is for 1 mole of bonds. And I want to get 1 specific bond. So I need to figure out how to do that. So this energy value comes from 6.02 times 10 to the 23rd bonds breaking. So that's what we've got to get into. So 1 mole of bonds is equal to 6.02 times 10 to the 23rd bonds. And then I have to take those and divide them. Okay, so I'm going to put that into my calculator. 542,000 divided by 6.02 times 10 to the 23rd. And that leaves me with 9 times 10 to the negative 19th. So it takes 9 times 10 to the negative 19th joules to break one bond broken. Okay, so that's just to get us to the point where we can even start the stinker of a problem. So the good news is now, though, I have my change in energy required. I've got my energy, I know Planck's constant, and so I can find my frequency. So like I said before, I like to do my algebra work before I put the numbers in. If you don't like that, that's fine, but I just think it's a lot less to write. So I want to find frequency this time instead of my energy. So I need to divide by Planck's constant on both sides so that I can get the frequency by itself. So my frequency is going to be, draw an arrow there. My frequency is going to be the energy, 9.00 times 10 to the negative 19th joules, divided by Planck's constant, which is 6.626 times 10 to the negative 34th joule seconds. Okay, so I'm going to put those two things into my calculator. And when I do that, I get a frequency of 1.36 times 10 to the 15th. And the units on this can either be 1 over seconds if you want, but remember that that is the same as seconds to the negative 1. Pick one, whichever one is your favorite, and go from there. So now I have my frequency and I can find my wavelength. So C is equal to lambda times nu. But now I know my frequency and I'm looking for my wavelength. So I'm going to divide by my frequency. My wavelength is equal to C over frequency, which is equal to 3.0 times 10 to the 8th meters per second, divided by my frequency, which is 1.36 times 10 to the 15th seconds to the negative 1. So like I said, 1 over seconds and seconds to the negative 1 cancel each other out. And when I put that into my calculator, I end up getting 2.21 times 10 to the negative 7th meters for my wavelength. If it's not specific, you don't have to put it into nanometers. And in this case, it's not. So we can just leave it like this. There is a lot going on here. I get it. It kind of stinks. However, it's one of those things that they're going to possibly ask you a question like this. They might ask it to you in a couple parts, but they could still ask you a question like this. So we've got to kind of go over it. All right. Hopefully this clears things up. If you find yourself still stuck, pop into a Google Meet and I will give you a hand.